Hello, everyone. My name is Igor from the Gravity Engraving channel. This channel is about laser machines and markers, equipment sales, training on laser markers using EasyCAD 2.0, and consumables for lasers, like lenses for M55, M79 with adapters, or M85 Step 1, specifically lenses for fiber lasers. I'll leave all the phone numbers in the description. Regarding WhatsApp, starting in 2026, some wonderful new laws are coming into effect in Russia, under which WhatsApp and Telegram might no longer work. So you can message me on, well, or starting in 2026, we'll use a number specifically for the Max Messenger. Max Messenger, the most wonderful messenger in the world. So today's topic is a bit different. It's about something else, the topic of color interference, that is, thin film interference on certain materials or specific metals. We achieved this effect in China on specialized equipment costing nearly 1.2 million, where our workpiece shimmers beautifully with color depending on the angle, the direction of the light rays, the crystal lattice, the engraving, the metal surface, the properties of the metal itself, and much more. This dog tag is about 2 months old now. I just washed it with some water, and you can see that it still shimmers just as it did a while ago. Let's zoom in a bit more. So this tag is doing great. It's perfect. It depends directly on its position. I mean, if we turn it like this, it all disappears. So its position plays a direct role here, but it's not specifically the diffraction grating that's at play here. There will be a lot of technical terms today, half of which I don't even know, but I've studied them, read up on them, and looked them up. Today's topic will be about diffraction gratings and the crystal lattice layer on the surface of stainless steel, which contains nickel and chromium, and achieving this kind of interference color. By interference color, I don't mean the colors that have formed on the stainless steel itself. Those are actually temper colors, but interference color is when, let's say, the third row of hexagons and the second and third from the right shimmer with different colors depending on the position or angle of those hexagons. That is exactly what color interference is. And in the same way, you can look at our hexagons here, which shimmer in that same rainbow-like fashion. It's very beautiful, very interesting. This is also interference color on our stainless steel dog tags. Everything you see here was done on MOPA M7 series machines. From JPT. Over here, we did everything on a machine from JPT Laser. We did a similar version on a JPT 60 M7 machine right here. So look closely. At a certain point, there will also be color interference, not as bright or saturated, but it's still there. See, that's how it shimmers beautifully. Yes, it's wear resistant, doesn't rust or oxidize, it has it all. On the machines, the LP series can theoretically do this too, but I've been doing slightly different things. This is exactly what's called a diffraction grating. When you have it on a polished tag, like right here, I could even see it. As they say, yeah, we can create these kinds of diffraction stripes. They shimmer beautifully at various specific angles and from different directions. In person, of course, it looks much more interesting because, well, light hits it from different sides. Plus, we're rotating it at different angles. And on top of that, the tag looks as if it's been polished. The same diffraction principle applies here as well. So the tag is polished, yet it shimmers beautifully. It's a similar situation with the JPT 60M7. Here we have two effects, including the diffraction effect. That's when the thin lines align with our little hexagon. At different angles and at the same time there's color interference, meaning light passes through the crystal lattice of our metal surface, and its glow changes or it's split into a spectrum, synchronizing there with other light that's coming specifically from the surface of our crystal, without passing through the actual crystal lattice on the metal surface. In short, it's quite a complex story, really. I think I've more or less conveyed the information. Today we'll be testing all of this on the JPT50M8 machine. If this kind of thing works out here, because there's already a specific algorithm for working with these materials. And if this actually all works out for us now, then we can basically achieve on almost ordinary stainless steel this kind of result. Naturally, each of you is going to ask, what the hell do we need this for? Well, it's for creating souvenir products with a unique, let's say, logo. I don't know, security features, basically making tags that no one else is making yet. Yeah, using a specific technology and algorithms on stainless steel. We have this little tag here today, a tag made of presumably 304 steel, polished. We'll be using the lens on the JPT 50M8 machine. With a 70 by 70 work area, I couldn't find a smaller one. Maybe it was just bought. The warehouse only has 70 by 70, 100 by 100, 150 by 150, 174 by 174, 200 by 200. I don't think we have any larger ones. I think there's even a 220 by 220. For the M8 series machines, the JPT50 M8. The ones that have this built-in head, if you're interested, feel free to reach out. Actually, the lenses will be available. They come with an M55 thread, and they install directly into the scanner head. Wavelength 1064 f100 with a 70 by 70 work area. Basically, everything here is as simple, clear, and logical as possible. The prices are reasonable. You can buy via the QR code. I'll also leave all the links in the description. Unfortunately, you can't do without ads these days. So let's start the machine, turn it on, and wait for it. We're setting up, preparing, and testing the focal length first. And then we'll start testing how well this function actually performs here. Let's go. Now let's look at what we've done. Basically, this is the result. I can't say how effective it is, but it's a result. Starting from the bottom left, we have the diffraction grating, which is 1,000th of a millimeter, then 2,000ths, and it increases from there. Did any change occur to the metal surface? No, it didn't, because that's how it was supposed to be. Now we'll make some changes to the parameters, run another test, and then we'll look at all of this together under the microscope accordingly and draw certain conclusions. I'll say right away that these experiments, it all takes a very long time. It takes half a day, a full day of time. And it's quite possible that after doing some specific experiments, I'll post it all later accordingly in the educational material. Everything done in EasyCAD 2.0 and in EasyCAD 2.0, everything done in EasyCAD 3.0 and in EasyCAD 3.0. And let's move on to further testing. Let's start perhaps with the interesting part, and then we'll end with the interesting part and with explanations accordingly, and we'll move on to the microscope. That is, work according to, well, let's say the algorithm that was supposed to work. Well, in theory, a diffraction grating was achieved here. In theory, we'll look further under the microscope. Different tests, different options. The same thing here. So, in theory, something supposedly worked out. And the diffraction grating seems to work, and everything is performing quite well. But again, that's theory versus practice. What we wanted to achieve, some significant result, color interference, didn't happen here. For many reasons. So it's possible we haven't reached the right condition yet, meaning more tests need to be done. Right here, we have something. But it's not a great result. And we switched to a slightly different method of working to obtain specifically just a diffraction grating and nothing more. There. So this is the result. I understand that we need to keep working. And now I'll make a video under the microscope. I'll conduct separately off camera a test with slightly different parameters like the ones I achieved on the GPT-67, and based on the results, I'll likely make an educational video. So we're working with a microscope from the company Tomlov. We're manually adjusting the focal length. Focus. In short, it's a pain in the neck, I'll tell you right now. Everything's twitching and wobbling. Let's start from the top, from the very beginning. So here go our cubes. Let me even say more. Let's start with this part. So we can see clearly that. Let's see, it should be higher. We can't see anything anymore. That is, the laser processing, you can see here that it only heated the surface of the material and did nothing else to it. And there are no lines here, no pulse interaction, absolutely nothing. And so, along the bottom rail. Accordingly, tests. You can see, again, look here, even given the density, at 2,000ths of a millimeter, each element still overlaps, which creates this kind of grid-like section. The further to the right, the less noticeable it all becomes on the stainless steel material. We repeat the processes, increasing the power, decreasing the power. So everything visible on the left side is 1,000th of a millimeter. For example, a fill density of 2,000ths. Our tracks are already visible, but again, only under certain parameters, a specific frequency and a specific pulse duration. Otherwise, the beam thickness will be so large that we won't notice it visually. It'll just blend in with the overall fill density. So, and it's the same thing. When we zoom in on the stripes again, our material no longer interacts with the laser under the same parameters. Let's move down a few rows. Same story. 1,000th, everything burns. Then 2,000ths, 3,000ths, 4,000ths. And well, the result is the same everywhere. So, to get a diffraction grading specifically, you need to work with a very short pulse duration, meaning in nanoseconds. Set the pulse duration as short as possible with minimum power accordingly, and to get a smoother track at a low speed, use a wide frequency range. This is just for your understanding. So, what do we have here? We can also increase the magnification. How is this done? Capture? No. Have to hold it. But when zooming in, again, we must understand that with this focal length, it's in manual mode, so everything is shaken here. So I'll say it again, the tracks are clearly visible right here. This is just for those who think beam width is one thing, while metal heating at a point or in a pulse is another. I think I've more or less explained it here. Let's set aside the first option, which, well, let's look at it visually. Something came out there. I can't say exactly what it is, but there's something. It glows somehow at certain angles. But that's about it. Moving on to the second option, where we started playing around specifically with changing the fill density again. So I added a whole bunch of parameters here, a bunch of lines, changed it all, engraved it, adjusted the frequency range, and the Q pulse. Consequently, it's turned into a complete mess here. It's even more of a mess here. And, well, as a result, we achieved nothing. So the first option, which was, let's say, conditionally mathematically calculated, was the best. Where we see nothing visually, we still, on the tags, we have these moments. For instance, here's a tag. The top part is supposedly completely empty. We put the top part under the microscope and see a very interesting image here. Let me even zoom in a bit now to try and see it at maximum magnification. Let's even probably lower the microscope like this. And I'll tweak the focal length here just a tiny bit. We'll even add some brightness and color if needed. Okay. I asked the Chinese guy to buy it. I said, a good microscope, 5,000 more expensive. On my dime, I'll pay for it. You told me there's no difference. Now I'm sitting here struggling and I feel like there could have been a difference. So, when buying equipment, never skimp on money and never listen to anyone, no matter who tells you there's no difference. That the machines are the same, it's all total bullshit. Anyway, it's poor but visible. Even if we engrave our product with the shortest possible pulse, we still get a very fine diffraction grading. A very fine one. That's a good plus, a good indicator. But visually, we don't see it. It doesn't work here for many reasons. Our machine isn't designed to create these color gamuts, to create, let's say, relatively thin light diffractions. Again, let's look at the line thickness. Here, it's already, if I'm not mistaken, 1/100th of a millimeter. Look, let's be realists. Given that it's 1/100th of a millimeter here, the distance between the stripes is approximately plus or minus relative to the magnification, so the stripe width is less, about 5 microns. So we can achieve engraving on stainless steel with a thickness of about 5 microns on MOPA series machines. And you can see there's already a slight color iridescence on this token. Moving down, at the bottom, I was trying to get a result, of course, so that all this was as visually noticeable as possible, but it turned out to be crap. So working on stainless steel is still possible by creating this kind of diffraction or a diffraction grating, right? Or a reflection mirror there, but visually they're very hard to see. Now let's move on to that very token where I actually achieved something extraordinary there, but I'll say right away that, again, the tracks aren't visible here in this case. You can barely see them here. They're there, meaning in some places they were displayed or engraved, let's say. Right. Moving lower, here you can already visually see our cobweb that formed. Let's try to tilt the microscope a bit lower, a bit higher now. There. And lower down, I just gave up on all that and switched to another mode, specifically the maximum pulse duration. And we started burning the metal. There. Consequently, we're getting some incorrect tracks here. In some places we get them, in others we don't get them at all. What's the deal? There should have been something. No, nothing, which is even weirder, of course. Let's try to run through it like this one more time. So it's finished, even though it's there. Basically, with a long pulse duration, we bake the metal until it's like a crust. Especially right here. The frequency range is clearly visible here. So a long pulse duration can occur at low frequency ranges. At low power, we get this exact metal baking. Working on metal in this mode isn't very interesting. Plus, with good beam quality, we get a clear plume of impact, like on the screen. The impact, I mean, of this plume on the metal is perfectly even. We get a clear. Everything seems okay, but I have to manually tweak it like this. With autofocus, it would be more interesting in that regard, but unfortunately, nothing can be done now. So you can see each individual pulse clearly. And with a size, for example, right here of about 2 hundredths of a millimeter, we end up with a spot size of approximately 2 hundredths of a millimeter as well. But you can see that they are overlapping right here. It's a bit unstable in places. You can see transitions like start TC, laser off, and end TC. So here, accordingly, and if we look at some other spots, we can even see the polygon TC processing modes. How they were processed? Right. I recommend a microscope magnification from 20 to 60, 100 max. Anything more, and you don't need that microscope. At other magnifications, you won't see or get anything interesting out of it. Let's also look at a density of 1.5 millimeters. Right here, we have 1.5, 1.6 millimeters. So 16, that's 16 thousandths, or 16 microns of dense fill. Here it's already a total mess under the exact same conditions. Everything's the same. Here we have about 17 to 18 microns. This one is already 19. And right here, it should be 20 microns. There we go. Now, for the most interesting part, we're moving away from our lens with the 70 by 70 working field. In other words, we didn't get the desired effect. Well, there's what we wanted, related specifically to, as they say, diffraction, meaning the change in structure, of the bands, lines, and so on. So that effect is there. There's an iridescent effect, a range of color tones. Not everywhere, but it's there. Look, for instance, the top cubes on the left side, the second one from the left. And there are similar effects further down that same row. So basically, there's something to work with. But let's switch to the lens with the 174 by 174 working field. The task remains exactly the same. Only now we're excluding our so-called diffraction mode and will, at best, get a mode where we bake the metal to a certain state, creating a crystal lattice on the metal surface. So when light hits it, it refracts and creates interference. Let's do a time lapse. It's a bit hard to see on camera, of course, but let's try to show it now. That very effect where we lose our diffraction and get a completely different result. Let's actually go ahead and turn off the light and try to find that angle, or maybe keep the same light but make it more diffused. So, this is the exact effect that most subscribers are trying to achieve when they want results, but it doesn't work out. So, by following certain modes, certain, let's say, settings and parameters, this can be achieved. Again, with a specific machine and a specific frequency range, the entire row from bottom to top turned out with this interesting iridescent shimmer. All right, guys, as always, this was Igor from the Gravity Engraving channel. So, I did a little test, so to speak, on working with dog tags, testing out different options. So, you don't always need to buy super expensive equipment like that for 1.2 million, though here it works in any mode with any parameters. And regarding this topic, we'll likely have a separate B2B where we'll do custom engraving on our polished dog tags. Maybe something like, let me show you how it looks. Something roughly in this format where the whole thing shimmers and, let's say, flows from one image to another. And with someone's logo, for instance, or something along those lines, we'll do the same thing across the whole tag so it all shimmers and flows beautifully in different colors and formats. So you'll be able to order ready-made tags with a background applied to the stainless steel surface, or lighters, a nickel coating, like mirror silver, or, well, I think we can do it on gold ones too. That's it, guys. As always, give it a thumbs up. Wish you all the best, lots of cash, and bye-bye.